So, torque. Torque is like the angular version of force. Definition of force that is applied at a given distance from a pivot point. And in physics, because we don't have F's anymore because it's a force, we dip into Greek letters again, and we use the Greek letter tau for a torque. And torques are measured in newtons times meters, and that's pronounced a tau. R is the distance in this equation, and it's also called the leverage arm. F is the force. And phi, which is just another way of measuring an angle, that is the angle between the radius and the force. So our first equation for torque, which is also a vector, is equal to R F sine phi. And if I draw a little diagram of this, if this is R, phi sits in there, and then this is the force vector. When we apply a torque to something, it will cause the object to twist, turn, or spin. So, as an example, I have a frisbee here. Let's see if this looks okay. And if I hold this part right here and push there, it'll cause it to spin in a circle. The further away from the pivot point that I push, the easier it is for me to move. So if you are trying to throw a frisbee, you don't want to hold in the center there. You want to try to hold on the rim to get the most torque on your frisbee. So for the example, it says which force is causing the greatest torque. Just like before, if we look here, one, assuming these are all equal forces, one is the closest to the pivot point. So one has the smallest radius, so it therefore has the least amount of torque. As we continue, 2 is far away, just like 3. So these both have the largest R. But the angles here are different. And sine of an angle, that function is greatest when phi equals 90 degrees. And since this angle is only 45, this is going to be the second greatest tau, second greatest torque, because phi is less than 90. We're kind of wasting a bit of our force because of the angle that we're using to move this object. Meanwhile, this is going to be the greatest torque because phi equals 90, and we have the largest of the radiuses. So to maximize torque, you want to increase the leverage arm as much as possible and then apply the force at a 90-degree angle to the leverage arm. This is why the amount of torque you can apply on something with a wrench depends a lot on how long that handle of the wrench is. That's very important. All right. So there's torques. We hopefully understand how that works for the most part. Moving on, next unit that we're going to try to make into an angular unit is going to be mass. So that our new term is going to be called moment of inertia. Moment of inertia is defined as the measure of an object's resistance to change to a spin. Just like how mass is defined as the resistance to change in an object's velocity. So we're kind of like switching that whole velocity to a angular speed, or a mega in this case, which is spin. Moment of inertia depends on the mass of the object, in addition to how the mass is distributed in that object. The further away the mass is from the center of the object, the higher the moment of inertia, and therefore the more resistant it is to a change in its spin. An example of that would be larger wheels. Larger wheels have more mass concentrated further away from the center of rotation, and therefore it takes longer or more energy to get it to spin. However, they are much harder to stop from spinning once they are spinning. Smaller wheels, in contrast, have a much smaller moment of inertia, and because of that, more mass is concentrated closer to the center of the wheel, and it will spin quicker, but it will also stop quicker than a larger wheel. Other examples of this, I apologize if I talk about this too much, but is disc golf discs. So I have 3 disc golf discs here that you can look at, and you kind of understand their job. If you look here, we have 3 disc golf discs, and you can kind of look at how much mass they have in each rim. So there. And you can kind of easily see the difference here. Where the blue disc is definitely the thinnest in its rim. The red disc is a little thicker, and then our yellow disc has a monstrous rim that's really huge. And you can basically judge how difficult the disc is to throw based on how thick the ridge is. This here is a putter. If you look at this, this is their speed rating. That's how hard you have to throw this disc to get to do what you want it to do. This is a putter, and it doesn't have a very large speed. So these things, they're easier to throw and get up to speed, but they will slow down much faster and have a much limited flight range because of that, because the angular momentum these things have, because of the rims, is much less. Our red disc is a mid-range. Mid-ranges have a larger speed. That is a 4 if you can't read it there. These are a little harder to throw than putters, and we'll go a little further, but they are not near as much distance as some of these discs like this one. This one is a speed 13 disc. This disc is very difficult to throw, but if you can throw it, it will travel very, very far because it has just so much angular momentum to it that it takes a long time for it to slow down when it's spinning. So it's going to fly a lot better. As we continue, there are 2 versions of how to do an equation for moment of inertia. The first version is the particle form, so this one here. And by the way, we use I for moment of inertia, and the units will be kilograms meters squared. The particle form is just the sum of all of the masses of the particles times the radius they are from the center squared. So when we do this summation here, it'll be m1 r1 squared plus n2 r2 squared plus m3 r3 squared, etc. This works for a small object if we have a few particles that we have to worry about, but as we start getting bigger, this equation gets more and more frustrating to use. There are other equations that can be found on book page 223, but you can use these ones here that take advantage of geometry to make your life a little bit easier. So for a sphere with the axis going through the center, the equation for I will be 2/5 mr squared. A cylinder axis, well, the axis through the center going down the cylinder is 1/2 mr squared. The long rod with the axis through the center will be 1/12 ml squared, where L is the length. And a thin rod with the axis at the end, so instead of rotating like this through the ball point, it's rotating like this. That will be 1/3 ml squared. And then finally, a thin hoop axis through the center will be 1 mr squared. Now, just like forces in linear forces, we can have multiple torques acting on a single object. And just like how forces can be trying to make something go right or left, torques can be trying to pull an object to spin different ways. Traditionally, make the call that clockwise is positive and counterclockwise is negative. And when we do have multiple torques acting on an object, we add them up. You can add or subtract just like a force, as long as they're, it works. And we use sigma tau, or net torque, to measure all those things together. And the net torque will cause the object to spin or accelerate angularly. And the formula is sigma tau equals I alpha. And if you think about what those things translate to in linear, they literally just translate into Newton's second law. So Newton's second law is also applicable in rotational physics. And over here we have moment of inertia be I again. So number 4, if the object is still and not accelerating angularly, then we can assume that sigma tau is going to be 0. This principle is used on the total beam balance or the doctor's office scale, where we are trying to balance torques in order to figure out things weight. Okay. We have 2 last variables that we need to translate into angular talk, essentially, and the second to last one is momentum. So definition of angular momentum is a measure of an object's rotational momentum. So instead of having just a one-way transitional or linear momentum, now we're going to talk about something spinning. There are 2 formulas for angular momentum, but we use the symbol L for angular momentum. The particle form, just like we had 2 versions for the angular momentum, the particle form will be L equals mvr. And we can also do a little bit of translation for this, where VR, V is just omega r, if we translate that into its angular form. And then we wind up with L equals mr squared omega. But if you recall up here, mr squared is essentially just the moment of inertia of a single particle. So we can also basically just say L equals I omega. So you can write this in 2 ways. You can use the linear forms of our variables, or you can use the angular forms. And both ways will work in a problem. So L, once again, is our angular momentum. R is the distance from our pivot point, or a radius if you want to figure it that way too. And then down here, as a reminder, omega is the angular speed. Right? The angular momentum occurs through the axis of rotation. Thinking of a bicycle wheel, the angular momentum would be going through the axle. It gives stability to rotating objects like spiraling football or a rotating bicycle wheel. That's why when you throw a nice spiral on a football, it doesn't fly chaotically. It stays very predictable in its trajectory. All right? And we're going to pick up from here in our final videos, just scroll on down and finish it out.